So why should you care about distributed systems today? So my name is Philip, and I want to start today's talk by answering that question. Because if we're going to learn how to build them, we should first understand why we build them. So distributed systems are the backbone of modern computing, particularly web scale. Because in a world that demands uptime, fault tolerance, and scale, we as developers, designers, computer scientists, we've decided that distributed systems are the answers. And also, the software and techniques that I'm going to describe today are actually at the heart of much of the popular software that you all know in this room, such as Kubernetes and Console. And even if you decide after today, as many of you probably will, to use someone else's distributed system, understanding how they are built and the trade-offs you need to make will make you a better programmer, a better designer, and a better operator of those systems. So there will be a slide at the end of the talk. I've asked the AV crew to leave it up for a few seconds, where you'll be able to get a link and a QR code to be able to download the whole deck. So there's no need to take any notes unless you want to. But I want to talk about what we're going to get, the three things that I'd like you to take away from today's talk. The first thing is, we're going to spend a couple of minutes understanding the unique problem that distributed systems present and how the Raft protocol addresses them. We're going to learn to integrate with a Raft library, integrate it with different storage systems using practical examples in Go code. And then we're going to look at some of the practicalities of developing, designing, testing, and managing that distributed system. So first of all, if you want to ask questions during the talk, the best thing to do is mention me on Twitter or X. This is my handle, and I'll do my best to answer the questions afterwards. Or I'll be around to talk later, but this can be a nice way, perhaps, if you have a question, you think of it right there, mention me on Twitter, and I'll get to it. So like I said, my name is Philip. I'm a software engineer with a particular emphasis on Go and distributed databases. I've been programming Go for about 10 years. I am also the creator of SQLite or SQLite, which is an open source distributed database built on Go, Raft, and SQLite. I also spent 2 years as a member of the core team at InfluxDB, which is a time series database written in Go and uses Raft. And I'm currently an engineering manager at Google, where I manage engineering teams who design and develop large-scale logging systems. Now, I'm talking here today not as a member of Google, but just representing myself, so it's important to note that. OK, so let's get started. Why are distributed systems difficult? In fact, there's only one really hard problem that we have to solve. And to gain an understanding of how the systems we're going to look at today, why they work the way they do, it's good to develop an intuitive understanding of what that problem is that we have to solve. So this is it. Say you want to set a piece of data to a particular value. It could be a row in a database. It could be a user in a user file. It could be a piece of file metadata. Or simply, it could be a key in a key value store. So this is easy. We all know how to do it. Make the call to your system. In this example, we're going to set x equals 5. But what if the data is really important? What if it's so important that we need to make multiple copies so that we don't lose it? Or we want to be able to serve queries to this data even in the face of network faults or hardware faults or bugs, something that happens in our system? The answer is we replicate the data. Now, this is simple, but it's good to understand why we do these things. So we decide we're going to replicate the data. So let's try one approach. We're going to build a system where we still write to one node, and that node will copy the data in the background and send it to node B. So this is great. It seems to solve the problem. But actually, it only appears to solve the problem. Because what happens if node B doesn't respond? Should node A respond with OK to the client still? Should it return an error? Or what if node B gets the data, but then there's a fault, and node B can't respond to node A? You see, it starts to get complicated, because what happens if your system suffers from what we call a partition, and the connection between node and B is severed? OK, so you decide to try a different approach. Another common method is to push replication responsibilities to the client. So now the client is responsible. But this means more work for the client, but it does give the client maximum flexibility and maximum insight into what is going on. But now another subtlety has been introduced here, because unlike the first system, in this system, each node in your cluster has to be able to respond to requests from clients. And that means each node in the cluster may get requests from clients. And if each node can accept these updates, you now must solve the problem if multiple clients come in at the same time with conflicting updates to the same piece of data. And if there is a partition, it's even harder to define what the system should do when X is red. Because when that partition goes away, you need to decide which value X is set to. Now, I don't want to pretend that there isn't solutions to these problems. Many of you are quite aware of them. My real goal here is to show you that there's actually a real problem here, and an apparently simple request, replicate my data reliably, consistently, and quickly, is actually harder to solve than a lot of people realize. Now, we wouldn't be here today if we didn't have a solution to this problem, which is known as distributed consensus. And decades of computer research have gone into solving it. And to a large degree, we actually have solved it. And one solution to it is the protocol we're going to talk about today and show how you can build with it. That protocol is Raft. So Raft is a protocol for solving the distributed consensus problem. It was created in 2014 by Diego Angara and John Ousterhout in Stanford. And one of its main goals was to create a protocol that was easy to understand and that would encourage system builders and programmers like all of us to build more effective and reliable distributed systems. Now, unlike a lot of talks in this area, I am not going to go into the details of how Raft solves the distributed consensus problem, because it's conceptually rather simple. I'm not going to go into the code and implementations and so forth. What I want to do is outline some of the core concepts of Raft, which will then help you hopefully understand how we're going to build the system in a few minutes. But I want to focus on the concepts and not the implementations. There are links at the end of my talk which allow you to really get into how Raft works. But concept number one in Raft is the log. Every node in a Raft cluster agrees on a set of events and the sequence of events, and this is called the Raft log. In fact, actually, the whole point of the Raft consensus protocol is to make this log the same on every machine. All other functionality flows from this fact. Raft has nothing to say about what is in this log and what each entry in this log represents. That's up to you folks to decide what each of these logs represents. All Raft will do is it'll make sure that each of these entries are applied to whatever state machine, database, storage system, file system, whatever it is you want. You decide what those operations mean, and it will apply them in order. Raft also defines a process called snapshotting. Now, what is snapshotting? The best way to explain is to understand what is the problem that snapshotting is set up to solve. So if the log is going to store every event that has ever happened to your state machine, and I'm going to use state machine, but by state machine I mean a database, a file system, but state machine is the easiest thing to say. What prevents that log growing without bound forever? Well, Raft has an answer. It's called snapshotting. What snapshotting is every so often, Raft will ask your code, your system, for an encapsulation of the entire state of your state machine. And then it will take that encapsulated state, and it will then delete every log entry that has already been represented in that state, in that snapshot. And that allows it to truncate the log, and now the state that Raft has is your snapshot and any log entries that have yet been applied. And that's how it stops the log growing without bound forever. The next concept is the leader. Raft is a leader-oriented protocol. Raft defines the leader election process, which ensures that there's one and only ever one leader in the cluster. And it is this node that is responsible for making sure the log is exactly the same on each node. Another important terminology is nodes which are not leaders are called followers. And finally, and just as importantly, Raft defines how we detect when a node has failed. And the mechanism it uses is called heartbeating. So they're the four key concepts. Before we get into the building phase, let's just see how those concepts solve the distributed consensus problem that we outlined earlier. First thing, for concurrent updates, well, now only the leader can make changes. Even if there are multiple clients coming into your system, they'll all end up going through the leader. consistency, the Raft log is key. The Raft log, the events in the series and the sequence of those events, is the authoritative record for what has happened in your system, and every node will agree on that. And fault tolerance, Raft only requires that a majority of nodes are running. So certain nodes can be down and your system can still run. It defines, as we said, failure detection via heartbeating, and it defines the leader election process. But the key thing to understand as system builders and programmers is Raft provides a solution to the distributed consensus problem. It abstracts away tons of the details, and it allows you to decide what state machine do you want to have replicated in a really nice manner. So what I want to focus on next is how can we build this? So now this is where I'm going to get into the meat of my talk. And this is what I mean by I want to create a map, a way for people to understand the Raft-based systems that they see out there. I'm not going to start with the code of Raft. Instead, I'm going to show you how to add Raft functionality as a building block. What we're going to do is we're going to walk through the conversion of a simple in-memory key value store, a map in Go, to a distributed version of itself, and show you the key code changes along the way. I'm not going to show you all the code that is required. I want to show you the key important things so that when you look at projects along, you're like, ah, this is that part and this is that part. So let's look at a system diagram for a very simple distributed key value store, one where the client attempts to do its own replication. Now, this system has one main goal. The client wants to replicate the entire set of key values to every node in this system, every KV block in that system, reliably, consistently, and quickly. Now, for those of you who know a little bit about this, it's important to point out one thing. This system is not sharding the key value space over the keys. This is an example where the entire KV store is replicated on each node. It is distributing for high availability and fault tolerance. There are some people who say this is not a distributed system, but they're wrong. This is a distributed system. It's just not sharding the key space, but it is distributing for high availability and fault tolerance, and it uses a distributed consensus protocol to manage that. Now, of course, this system, I would never build it because this system suffers from all the problems that we outlined earlier. What do you do? What does the client do if some nodes don't respond? What is the mechanism for resolving conflicts if two clients come in and set the same key to different values? But this is where we start. So let's take a look at some very simple Go code which would implement one of these KV stores, the HTTP layer and the KV store. So here's the Go code that runs in each node, at a high level, obviously, with many, many important coding details removed. The API for one of these nodes is given as an example above through a curl request. Set user one's name to Batman. We have a type called KV service. What does it have? It simply has a map, string to string. And then we have a HTTP handler. Most of you should recognize the signature of this. What does it do? It reads the post request off the wire, unmarshals the data, and for every key in the request, it updates its local map. And every node would run this code. Now let's start adding Raft to this to make it a distributed, fully replicated key value store, and see how it changes the system design and see how the code changes. First of all, let's start with a conceptual design. Conceptually, this is what we're going to do. Now, it's important to understand that I don't consider this a system diagram. That will come in a minute. Instead, this is a conceptual diagram. I'm trying to get across what is actually going on in the system so you can understand the code in the distributed KV store that we're about to build. Clients now write to a Raft black box. This black box accepts operations, KV sets, and takes care of pushing them out to the cluster. It tracks which nodes have received the changes. It tracks if a quorum, i.e. majority, has been met, and anything else that needs to happen. Node failure, leader elections. It takes care of all of that to make until your change is safely replicated to the cluster. And only when all this has happened does it respond back to the client. So from the client's point of view, nothing has really changed, except that it's much simpler to work with this KV store. The client will either get back OK or it'll get back error. If it gets back OK, its change has been replicated safely. If it gets back error, it has not been replicated at all. There's not going to be any in-between states. It's not going to find that some nodes have it and some nodes don't. This is the beauty of Raft. Now, how do we go about actually adding this Raft building block to our KV store into the code that I just showed? So let's start by introducing one of the best known open source Go implementations out there, the Raft library from HashiCorp. So why do I choose this library? I've been working with it for almost 10 years. It's a mature implementation now in Go. As I said, I've used it for 10 years, as many others have. It powers Console and Nomad. And so these are systems that are run in production by companies every day. So that's another vote of confidence in it. It's got pretty good documentation. I find the documentation quite good, as many Go projects have, but it's got good documentation. Quite customizable. If you have a special use case that needs Raft to work in a certain way, there's a lot of hooks in the way you can customize it. But for years, I've been developing SQLite for almost 10 years. It's only in the last 6 months that I finally really had to use these customizable options. So you won't need to customize it, but it's there if you need it. And it's also MIT licensed. Now, I call this out because, as many of you may know, HashiCorp changed the licensing on their open source products recently. But this library remains MIT licensed. 1.5 is MIT licensed. There's no indication that's going to change. But 1.5 is available for use, so there's no concerns relicensing. I'm not a lawyer, but it's still MIT licensed. So now let's look at some code to give you an idea of how we're going to integrate the previous KV code in with this. Here's our new code that shows our distributed KV store, and let's look at what's changed. We have a new variable added to the KV service, a Raft consensus subsystem. We also have made a really important change to the HTTP handler. It reads the request as before, but then that's it. It takes those bytes and it sends them through the Raft system and waits for a response from the Raft system itself, success or fail, and responds to the client. If everything went through, it'll get 200 back to the client. If it didn't, then it'll return with an error. One thing to understand is the code I'm showing here at the bottom, it is code that runs on the whatever node in your cluster, or actually I should say, it is code executed, because the code exists in every node, but it is the code that is executed on whatever node in the cluster receives the request. Now let's look at the code that is called on every node if this operation has been pushed through the Raft subsystem. Think of it like this. This is the code that executes on the front side, the side of the Raft block that is nearest to the client. Let's look at the code that executes on the other side of the Raft block that executes on every node, assuming the operation made it to consensus. This is what we have here. This is another apply function, but it's a different apply function. It is, if you will, like I said, called on the other side of Raft. Look what it's doing. It's very similar to what the HTTP handler did before. It gets a set of bytes. Now, they have to be encapsulated in a new type, but that's an implementation detail right now. Pulls those bytes out, unmarshals it into a map, and then applies it to its local key value store. So you see what we've done. We've conceptually inserted the Raft code in between those two key points that were in the HTTP handler in the simple version. The other thing to notice is that the Raft system is instantiated with a network resource. There's a lot of details missing from this, but the main point I want to get across is notice how we have added a new system to your code, and it requires a network resource. This should tell you that these Raft nodes are now communicating with each other over the network. This is a system architecture diagram of what we've just built for our distributed KV store, and is a much closer representation of what would actually be deployed in a physical system. So this system exists today. I built it actually a long time ago. It still works great. It's a demonstration of using HashiCorp. It's called HRAFD. It's available up in GitHub. And in this diagram, every node is communicating with every other node, or at least has a network connection open over the network. And each node, being the green nodes, is running a Raft consensus module. Each node is also exposing an HTTP API for clients to send KV updates. And that's it. And now let's see what happens. First thing that'll happen in this new system diagram is a client comes in, sets a key, it sends it to the leader. We'll talk about that in a few minutes, but it sets a key operation to the leader. The Raft subsystem on each node will then take that operation and ensure consensus is reached for that operation. Assuming consensus is reached using the Raft protocol, then and only then is the change applied to each local KV store, and Raft invokes this. And this is where the apply function that we saw earlier kicks in. So the great thing about this is Raft has taken care of so much for us. It handles node failures, leader elections, it's invoking snapshotting when it needs. Everything is taken care of. You just need to decide what's the API that the client has and what is the store that I want to modify using distributed consensus. One more detailed slide, and then we'll be back to the architecture diagrams. This is more for completeness, but what I want to show what this is, these are the 5 functions that you must implement to integrate with the HashiCorp library. Don't worry too much about the details. What I really want to do here is to give everybody a sense of what you need to do to integrate your data, your state machine with the HashiCorp library. The first function you have to implement is apply. We already talked about that. Since you will decide what state machine, database, file system, whatever it is, key value store, that you want to run under consensus, you decide that. So you must tell Raft how to change your system. So you implement apply. You also implement snapshot. Again, you chose the state machine, so you must define the process for how to encapsulate that state machine. Let me give you an example. Imagine the state machine is a SQLite database. I'll actually show this example in a moment. One simple encapsulation of the SQLite database is open up the file, read all the bytes off the disk, and that's your state. That is, in other words, the entire SQLite file at a moment in time. The other thing you must do is persist. Snapshots must be stored permanently, persisted to disk for a period of time. You implement how this happens. You get a lot of help from the Raft library, but it does give you the option of controlling how your snapshots are persisted, because some people might like to do things like persist them to S3 so other nodes can pick them up. Another really important function you must implement, restore. Restore is the opposite of snapshot. Why do we need restore? You build one of these clusters, your favorite key value store. It's a 3-node cluster. It's running for 5 days. There's been lots of snapshotting. Therefore, lots of entries have been deleted from a log. You decide to add a 4th node. How is that node going to get its state? How is it going to catch up and be a full copy of the data? It will be given a snapshot by one of the other nodes. Therefore, you need to be able to reverse the snapshot. So taking my SQLite example, you would get all the bytes of the SQLite file that's written from another node, read from another node, and write it to disk locally. That's restore. That's just an example. So it's the opposite of snapshotting. And then other log entries would be applied on top. Finally, there's also release. It's not a function I use that often. It's a technical one. You can look into it. I've never needed to use it, but it is a 5th function. It's often a no-op. But that's to give you a sense of the amount of work that you have to do to integrate with this great library and bring distributed consensus to your system. So to really learn this lesson, let's do 2 more systems. Let's see what changes, and let's see what stays the same. So let's make a distributed version of BoltDB. Many of us as Go programmers, many of you will have heard of BoltDB. It's a well-known key value store written by Ben Johnson of Lightstream fame. In this case, the system design almost stays the same, but the storage system to which Raft will apply the events has changed to BoltDB. The client comes in, it'll say, set this key, the leader will accept it, the leader will negotiate with the rest of the nodes, make sure it's in consensus, and then Raft will call apply. Let's look at how the code would change for BoltDB. So at a quick glance, this code actually looks roughly the same, but let's look a little bit closer. Instead of having a map in memory, we now have a handle to a BoltDB instance. Yes, it would have been initialized elsewhere, but now we have this handle. And then in the apply function, the function that is called on every node once consensus has been reached, now doesn't change the map that each node has. Instead, that node calls functions on the BoltDB handle and sets the key. So I hope you can see what's going on here. Each node has a handle to a different type of service or storage system. In the apply function that's called by Raft, each node has to do something slightly different. But notice how the set key handler hasn't changed at all. It gets a stream of bytes that represents a request. They're sort of opaque to it, pushes it into the Raft system. Once the Raft system has reached consensus, the Raft system will call your special apply function that interprets those log entry bytes as meaningful and changes your system. Let's do it again. Let's do it with SQLite. Let's use Raft to turn SQLite into a distributed version of itself. Again, the system design looks very similar. There are a couple of interesting differences, though. First of all, this time the log will contain SQL statements. This is basically how SQLite works. Now, one thing to notice is this is statement-based replication. And so for those of you that have been paying close attention, you may already see one implication of this. Statement-based replication means that non-deterministic SQL could be a problem here. What if a statement has random? That will be evaluated differently on each node at the apply time. If If you understand what I'm saying, you already have grokked a lot of what we're talking about here today. But it's not a big deal. There are ways to work around it. I'd like to talk about this more, but I just wanted to flag it, and it's a good discussion for Twitter. But let's get back to really what's going on here. Let's look at how the code has changed now that we've swapped out BoltDB for SQLite, and let's look at what hasn't changed. Again, at first glance, it looks quite similar. Let's look at what's changed. Instead of having a handle to BoltDB, we simply now have a handle to SQLite. And in the apply function, instead of calling functions on the BoltDB instance, we make calls to the standard Go library to execute the SQL statement. So I hope you're beginning to see the pattern here. Raft provides the distributed consensus, the log, the leader, failure detection, leader election, and you decide what goes into the log and what should happen to the state machine on every node if an entry in that log has reached consensus. Okay, so this brings me to the final part of my talk today. So we're going to talk about developing and running these systems in the real world. Now, much of this talk has been influenced by my experience building SQLite over the last 10 years or so, but the principles are exactly the same. As I said, SQLite is based on exactly the same libraries we spoke about today, and SQLite, and has been, of course, is written in Go. Testing. The first thing I must have to say, I have found testing in Go to be a great experience. I'm continually surprised at the amount, this is a personal opinion, I'm continually surprised at the amount of Go code I find that's tested using libraries that are not the standard library. I've always found the standard test library in Go very, very useful. So, and I've written some really nice tests and I'm happy with it. But let's talk about testing for this. Let's say you want to build a system just like what we've outlined. You've picked your favorite system, your favorite database, your favorite file system, and you want to put a distributed consensus layer on top. Comprehensive and quality testing is really important for the complicated and racy systems that we have just described here. So I want to talk about the testing approach that I have found effective if you build a system like we just spoke about up here. First of all, unit testing is a fundamental approach. In fact, if you're, I'm sure some of you experienced this, if you can't test a component of your software easily and well without having to mock too much stuff or without having to bring in too many other components, it's often a sign that your module is maybe doing too much or its interfaces are not well designed. But most of the store level, most of your storage system level can take place at unit level testing. And why do I say that? I say that because the systems that we have just shown here are shared nothing systems. You can do reads and writes to that node just using the low-level layers of the software that you have implemented. In other words, you can test the storage system and perhaps a thin layer on top. These are not systems, because they're fully replicated, that require queries to hit multiple nodes, bring data back, map, reduce it, merge it, none of that, right? It's simple to test in that sense. So all the storage level testing can take place at this level, your reads, your writes, and so forth, invalid queries. Next comes system level testing. This is where you can test Raft level interactions. Sometimes it's called integration testing. This level of testing should focus on the replication of entries to each node. Can you join nodes together? If you drop off one node, is the cluster still running? If you bring that other node back, does it catch up on the entries that were written to it while things happened, while the other node was down? Read consistency, leader election. This is where all the Raft interactions take place. But because it's still Go level testing and Go unit testing, this testing can still be very fast if your modules are well designed. Finally, though, there is still a place for limited end-to-end testing of these systems. Now, this is distinct from performance testing, which does require full systems to be deployed. But in my experience, you want to be careful about adding end-to-end testing for these systems. You need it, but it should be very deliberate and only for test cases that cannot be executed in any other way. Why do I say this? I have a lot of hard experience with this in other databases. A lot of people make a mistake of writing huge end-to-end test suites at the start because it's a great feeling when they pass. You're like, wow, I have tested my database from top to bottom. I know it's in good shape. But the moment one of those tests start failing, it's so time-consuming, it's so costly to debug it, especially as your development teams are growing, because knowledge starts to weaken. So you be very careful about end-to-end testing. It is important, but it should be limited. What I use end-to-end testing for SQLite is basically a smoke check. I launch real processes. This is the one test suite I have that is written in Python. I launch real processes, make sure that they start, make sure that they cluster. It's basically a smoke check. Once I made a release that passed all the unit tests, all the system tests, but it wouldn't start because it needed a small bit of writable disk somewhere, which hadn't been checked anywhere. So this is partly to save me the embarrassment of ever pushing out a release again that doesn't actually start. But it's very important. The other thing to notice is I follow the testing pyramid philosophy quite well. Many of you may recognize this. And it really does work. If you do your testing as close as possible to the components, it's much faster, much more effective. As reference, here's the source line count from a version of a couple of years ago from SQLite, the last time I gathered the numbers. At the time, so SQLite is on version 7 right now. This was version 6. It was about 36,000 lines of source code. 10,000 of those lines were unit tests. 7,000 lines were system-level tests. And I had less than 1,000 lines worth of integration tests. So it really is a pyramid shape, and it's actually worked out well. The pyramid testing philosophy certainly works. Accessing and managing your cluster. Very important. If you get excited, you build one of these systems, you have a really good idea, you want to build something and add Raft to it, you want to push it to production, there's 3 or 4 things that are important to understand that are particular to these systems and can trip people up at the start. First thing, clients must be able to find the leader. Somebody wants to make a change to your distributed system. In the systems I've just built, they've got to find the leader because all writes go through the leader. So the first question is, what mechanism am I going to use to have the client find the leader? The client doesn't actually have to know where the leader is. Why? Because every node of the cluster knows where the leader is. All your client has to do is find the cluster. And the node that it hits, if it's the leader, great, problem solved. Leader does the write, everything's done. But if it's not the leader, if it's a follower, the follower has a choice. The follower can respond to the client and say, I'm not the leader, but the leader's at network address 1234, or a HTTP redirect. Early versions of SQLite used to do this. But a more sophisticated solution is for the follower in your distributed system to forward the request transparently to the leader, wait for the leader to process the write, get the response back from the leader, and then send it on to the client. And if you're building a production system, it really is worth putting that extra hop in. It makes the system so much easier to use. And like I said, transparent forwarding is what SQLite does today, and what most production distributed databases will do, even if they're not built on Raft. The next thing to understand when building one of these Raft-based systems is very important. Adding and removing, but adding in this example, changing the membership of your cluster requires consensus. You wake up one morning, you find your cluster is down. We don't like it, it happens. So 2 out of your 3 nodes have failed, and a quorum requires 2. So you start spinning up new nodes and try and add them. It doesn't work. Why? Because Raft specifies that the membership of your cluster itself is an operation that has to be managed by consensus. So to manage nodes in your cluster needs to be up. Now, there are emergency repair mechanisms. SQLite has them, as does Console. They're not specified in the Raft paper, but Raft specifies that cluster membership requires consensus. So that's another thing. Other interesting point is, I've said that writes require the leader, but reads do not. Any node can serve as a read request because the node can just hit its local state, it has the entire state of data, and respond to the client. Whether you want that to happen depends on the read consistency levels that you want to offer to your clients. Remember I said that if you build these systems, you'll gain a much deeper understanding of what these terms mean? This is your chance. If you want to guarantee to a client, or the client wants to make sure that the read that it does includes all the writes that happened before, then it has to go to the leader. But if you're prepared to tolerate some data staleness, any node can service your read. So that's the last thing. What does your application require? Can you satisfy your reads from followers? Monitoring your Raft-based system, another very important topic. You build one of these systems, you put it in production, your team wants to know what should they monitor. Monitor all the usual suspects, CPU, RAM, disk. But if you build something on top of HashiCorp Raft, and this may apply to other Raft systems, but definitely if you build it on top of HashiCorp Raft, disk is what you want. Why is that? Because every time it writes to the Raft log, it does an fsync on all OSs. And so if you create a cluster and hammer it with write traffic, it will be the disk that saturates first. Now, if you decide to deploy Raft, as I did once, or SQLite, as I did once for fun around the world, and the network travel times between your nodes start getting up to 100 milliseconds, then probably the network is going to become the bottleneck. But in a more realistic scenario, you're probably deploying this in a data center. Maybe each node is on a different rack. The disks will be what will peg first. So if you want a high-performance system, start focusing on the disks first. The other thing to monitor is, of course, the nodes themselves. If one goes down, replace it, and so forth, standard stuff. But there's two things in particular to the HashiCorp Raft system you should watch out for. The first one is node startup time. This is interesting. And I didn't get caught up by this for quite a while. But when a node starts, when it's built on Raft, it has to reapply in principle the whole log from start and apply it to your state machine to bring that state machine back up to the place it was before the node exited. If you have a lot of entries in your log, it can take a while for those all to be applied. And they all have to be applied before your node is ready. Now, in practice, what usually happens, you'll have a snapshot and some entries. So the snapshot is put in. That's usually a very quick operation, and subsequent entries are applied. But still, you should monitor your node startup time, because it can take a while. But one way to make them fast, one way to shorten your node startup time is to do a lot of snapshotting. But there's a problem with that. There's a trade-off. Because the other thing you have to monitor is node snapshot times. Remember I said that Raft needs to snapshot your system every so often, unless you want the log to grow without bound? There's a critical point in the snapshotting process where Raft will block changes, block writes. So you want your snapshotting process to be as short as possible so clients can write. That window when clients cannot write is as small as possible. Now, I just said a moment ago that frequent snapshots were a great way to address the long startup time. But frequent snapshots are also a way to stop writes periodically. Now, all these problems can be solved. They will take more complex programming than what you will see in HRAFD. But a lot of these approaches have been applied to SQLite and other systems, presumably console as well. So there are two things to watch out for. And monitor. I make liberal use of the XVAR variables. It's good, and plenty of logging. Now, I'm approaching the very last part of my talk, very last slide, or second last slide. So many of you are probably sitting here today, and you're probably thinking, so after all of this, is a Raft-based approach the right approach for the system I want to build, the software project I want to develop, the product I want to build? There are some final considerations to take into account when building with the HashiCorp library, and actually Raft systems in general. And one way to make this decision is to look at now the potential costs and downsides of using Raft. First thing is latency. So there's nothing for nothing in this world. If you think about it, your write goes into the leader, and the write bounces a couple of times, the operation bounces a couple of times between nodes in the cluster, so consensus can be reached. But that introduces latency. So you can expect your write performance to change. It's going to go down, right? You're not going to be able to write to this system as fast as you did before, possibly by 1 or 2 orders of magnitude, depending on the hardware that you have given. But of course, you get a lot in return. Batching can help. If your clients can batch up a lot of their operations in one go and then send them to the Raft system, then you can actually get write performances is just as good as before. But now the clients have to batch requests, and then there's going to be latency at that point. So the first thing to understand is your write performance will be quite a bit different. The second thing you want to decide, perhaps, and this may actually make Raft usable for you, is do you want to have a control plane system or a data plane system? What I just built up here is a data plane system. This is a system where everything goes through Raft. Configuration changes, node membership, cluster membership changes, and of course the data itself. But you do not have to take that approach. You can build a system where just a small amount of data, perhaps data that's critical to your system, has to go through Raft. Let me give you an example. In many databases, the really important stuff is what nodes are in the cluster and what files live where. That is an example often of data that every node has to agree with. But what data is in those files may actually not have to go through a consensus system. Time series databases are like this. It's not the end of the world if not all points make it or if they change a little bit. So what you might do is you might just decide to take Raft and apply it just to your core configuration system for your distributed system. But then the write traffic hits a node in your cluster, goes straight to disk, or maybe takes one hop and goes straight to disk, because the configuration tells that node where the data should be written. Now, you may get some eventually consistent queries when you query the data, but maybe that's OK. So perhaps you can't use Raft for your data path, but you can still use it for your control plane. The last thing to think about is, and this might be obvious to many people already, let's take the systems that we've just built. The write performance will not scale horizontally. Throwing more nodes at this system will not make it write faster. Why? Because all writes go through the same node. The only way to, at least for a data plane system which you showed up here, the only way to make it go faster is to throw more hardware at each node so that whatever node is getting the write can make that write faster. So better CPUs, much better disks, faster networks. That's the only way that you can increase write performance. Read performance is different. Because any node can service a read in principle, depending on your read consistency requirements, actually adding more nodes can increase your read performance. Excuse me, but in my experience, read performance is usually so fast anyway that you're not really as worried about that. But you could add more nodes, and you will increase your read performance as long as you can tolerate some read consistency changes. That's the other thing to think about. There's a couple of other things. Raft is not a good system where thousands of nodes are coming and going. I've had more than one person approach me and tell me they'd like to run SQLite on all the cell phones in the AT&T network, and I say that's not going to work. So it depends on your use case. If you look at where has HashiCorp Console, which uses this library, been successful? Or etcd, which is built on a different solution, but is built on Raft. It's for where you want to store some key data that is critical to your system. Now, however, more recent versions of SQLite, I've actually started changing it so that it can actually support very large data sets, hundreds and hundreds of gigabytes. But it's still targeted towards, you have a set of data that is very important to be correct, and you might be running 6, 7, 9, or 12 nodes. But it's not really going to work for 50 nodes. So these are the things to think about when you want to decide if Raft is a system for you. So that is my talk. We wanted to talk about 3 things today. We examined the core challenge of distributed systems, the one hard problem they have, and how Raft solves them. We dived into the integration of Raft with 3 different storage systems using the HashiCorp Raft library. And I hope you all gained some practical insights for developing, testing, and deploying your own monitored system. And now I hope you all can answer the question about why distributed systems matter today as well. So thank you very much.